Good afternoon, ladies and gentlemen. Welcome to Bruker Nanosurfaces webinar on AFM-based conductivity measurements. My name is Siu Ting and I would be hosting today's webinar. Before we commence, we would like to share that all attendees would be on listen-only mode. There is an opportunity to interact with us and we encourage you to ask questions in the questions window. There will be a 1-hour presentation followed by Q&A, which our speaker will answer at the end of her presentation. If we are unable to respond to all your questions due to time limitation, we will respond to you through email. Without further ado, let me introduce our speaker for today, Dr. Jiang. Dr. Jiang is the product specialist at Bruker Nanosurfaces, responsible for application and technical support for metrology instruments in Southeast Asia. She has more than 8 years' experience in atomic force microscopy characterization techniques and extensive experience in both applications support and hardware support. Prior to joining Bruker, Dr. Jiang obtained her Ph.D. in Chemical and Biomolecular Engineering, National University of Singapore, and she was a research fellow at the Division of Bioengineering and US after graduation. She has over 10 peer-reviewed publications and conference presentations. We now invite Dr. Jiang to share with us AFM-based conductivity measurements. Dr. Jiang, please.
Good afternoon, everyone. My name is Jiang. Welcome to the webinar today. My topic of the webinar is AFM-based conductivity measurement. Here is the outline of the contents we are going to cover today. First of all, we understand that users may face some issues and frustrations when you do the AFM-based conductivity measurement, and we will discuss several commonly seen issues in detail. After this, we will discuss the solution and optimization techniques in AFM-based conductivity measurements in the following 5 areas, including probe selection, sample preparation, selection of imaging modes, optimization of settings, and hardware considerations. If all the above solution and optimization techniques are not able to fulfill the requirement in your applications, we will provide alternative solution, which is the recent development in nano-electrical measurements enabled by peak force tapping technology. We will cover both theory and application examples. Many users who do the AFM-based conductivity measurements may suffer from the following issues. The major issue is the poor tip sample force control, which is high, shear, or normal forces between the tip and the sample. Because of the poor tip sample force control, it brings several issues. For example, the AFM tip may destroy the soft materials understudy or push and pull away loosely bound samples. So it's not suitable for study of conductive polymers, soft conductive materials, or loosely bound samples. Another aspect of the poor tip sample force control is that the AFM tip may be worn off and the front side conductive coating is gone. Because of this, no conductivity signal will be going through the sensors and there is no signal. Due to the high force, user can also encounter repeatability and resolution issue because the resolution is highly dependent on the tip radius. Lastly but not least, larger current passing through the sample can damage the samples. Before we talk about how to solve the issues that we mentioned earlier, we need to understand the working principle and some terminology and terms that user may feel confusion about. CFM tuner, TR tuner, and PF tuner. CAFM is short for conductive AFM. Tuner is short for tunneling current force microscopy. And TR tuner is short for torsional resonance tuner. PF tuner is short for P-force tuner. CAFM is usually used for high conductive sample, and the current range is usually from 1 picoamp to 1 microamp. Tuner is short for tunneling atomic force microscopy, and it is usually used for high resistance sample, and the current range is from 80 femtoamp to 120 picoamp. For TR tuner and P-force tuner, we will cover it later on. In the all above AFM-based conductivity measurement, they share the same common working principle. First, a conductive tip is in contact with sample surface, either in contact mode, P-force tapping mode, or TR mode. A bias voltage is applied to the sample, and the electrical current going through the amplified and measured. After understanding the working principle, it's not hard to identify the areas of solutions and optimization technique in AFM-based conductivity measurements, including ProSelection. We need to consider the spring constant and the front side coating specifically. Second, sample preparation. Because the sample bias is applied through the system to the sample top surface, we need to make sure that the continuity between the top surface to the chuck. The third one is the selection of the imaging modes, followed by optimization of the settings, especially the contact mode, and hardware considerations, including the accessories and the application modules. Probe selection. The requirements of the probe for current conductivity measurement is that the tip front side coating must be electrical conductive. It's better to have the resistance to tip wearing, and the spring constant must be suitable to your application or the sample hardness. Here, I list several highly common used probes for your selection. The first category is SCM-PIT and SCM-PIC. They have the front side coating of platinum iridium, and they are widely used for semiconductors, metals, ferroelectrics. MESP has a coating of cobalt chromium, and they have the same applications in the above. But they, compared to the SCM-PIT and SCM-PIC, they have properties of more resistant to tip wearing. DDESP and DDESP-FM is boron-doped diamond probes. They usually used for hard materials such as DLC or soft materials, semiconductor devices, MEMS, biosensors, so on and so forth. Compared to the above conductive coating probe, they are more resistant to tip wearing. If all the above probes are not good enough for you, we have the Rock Mountain series probe, which is the solid platinum wire. The spring constant is ranging from 0.3 to 18 Newton per meter. They have the excellent conductivity and wide applications. Sample preparation. After we select the proper probes for the sample, on the study, we need to pay attention to the sample preparation. Here, I recommended the 3 steps for you to prepare your sample. The first one is you need to glue the sample onto the sample pack using either silver paste or conductive tape, and make sure that the sample top surface is bridged to the bottom metal pack. The second step is you need to confirm the electrical continuity between the sample top surface and the chuck using the multimeter. The third one that you need to pay attention is when you're measuring the large samples, we recommend use of an electromagnetic interference shield hood. Large conductive samples can act as an antenna and focus electrical noise from the environment into the input of the tuner sensor. Sample preparation. For very conductive samples, you need to limit the current so that you can still use the tuner module that you have. You can solder a resistor to limit the current as shown in the picture here. Basically, the sample, the resistor, and the sample pack make a series, and the Kapton tape is an isolation film. Most AFM-based conductivity measurements are based on contact mode imaging. Next, we will discuss how to optimize the CFM and tuner imaging settings. No matter which application module you have, the first step is always to get decent AFM images. To do so, you need to adjust the set point to make sure the sample is engaged on the sample surface. And you have trace and retrace profile identical. Slow scan rate is always desirable. In addition, you need to adjust the P-GAN and I-GAN, and they need to adjust such that the deflection error channel spikes are within minimum range and the noise level is acceptable. After you get a decent image, you need to pay specific considerations for the conductivity measurement. To increase the tip contact time, you need to slow the scan rate. And you need to get good enough force to get the current, because the current can only be measured when the tip and the sample in contact. Of course, you don't want to use high set point because the tip wearing will affect your current measurement as well. The third one is you need to select correct current sensitivity and apply proper sample bias. The trick is that you need to always start from a small sample bias, and depending on the sample properties. For example, if you use dielectrical materials, you always need to start use low sensitivity. And for high current, for high conductive sample, you can start from a high sensitivity. For tuner and the contact mode, we have both open-loop tuner and closed-loop tuner. Here is an example of the image taken on the floppy disk. The left side is the high sensor image. Okay. And the right side is the tuner current image. As we can see here, the bright region is more conductive area, and dark region is the less conductive area. In contrast to the open loop tuner, the closed loop tuner is actually, we fix the tuner current value while we use the adjust the sample bias to maintain the tuner current. So we look at the feedback bias channel, and the dark area is actually the more conductive region, and the less conductive region is bright area. Here is the parameter panel of the open loop and closed loop tuner parameters. To switch between the open loop and closed loop tuner, we need to just click the feedback mode, disable or enable. Both standard and extended tuner can be operated in open loop and closed loop mode. However, due to the strong capacitance between the tip and the sample. Measuring with standard tuner or with high gain settings in extended tuner may not be able to yield the desired result. As the voltage changes rapidly, it is possible for the feedback current to become greater than the current being measured. Therefore, using low gain settings in extended tuner is recommended when operation in closed loop mode. In addition, you can also limit the sample bias in here, and you can also change the feedback eigenvalue here. Point and shoot IV curve. In addition to the imaging mode, the tuner or CFM modules also have the capability of measuring local current IV spectral using the spectroscopy mode. In order to obtain the IV spectral, the imaging scan is stopped and the tip is held at a fixed location while the sample bias is ramped up and down. In spectroscopy mode, the feedback is switched to contact mode. A constant deflection is maintained by the feedback while the sample bias is ramped. This assures tip sample contact is fixed while the IV curve is taken. The resulting current through the sample is plotted versus the applied bias. The IV curve can be also taken using the point and shoot feature. The point and shoot feature offers the option of drawing a line or a box on an image, defining a number of points, and then the FM tip will automatically move to those locations to capture one or multiple IV curves at each point. While this is a powerful automation feature, it often can be more useful to manually choose a few spots of interest at the specific regions of the sample. And here is the point and shoot parameters window. The window here is a high sensor channel or current channel. Point and shoot can capture ramp curve on multiple design locations on a saved image. In the saved data, force curve or the IV curve are linked with AFM image for easy offline analysis. In addition to the contact mode imaging, users may use or may hear about the torsional resonance tuner. Actually, TR mode can be used for the conductivity measurement as well. In TR mode, the FM tip is vibrating in horizontal direction, driven by two piezo's of the piezo's at the probe holder. The TR mode interaction occurs entirely in the near field, so it can be used for the tuner measurement. The tip remains at a constant distance to the surface at all times. For soft materials such as DNA, closed deposit materials such as carbon nanotubes, the TR tuner can be a candidate. But because of the tip sample contact is changing and the TR amplitude is small, there is always a stability issue. Plus, the operation is relatively difficult, so not so many users choose this mode for the current measurement. As for the hardware and accessories, here are the photos Bruker supplied application modules for conductivity measurement. Here is the CAFM, here is the tuner, and this is the tuner 2 module, also called extended tuner. For CAFM and tuner 2 module, they have 3 ports for offset and gain adjustment. For tuner 2 module, they have, in addition to the 2 sensor port and a test bias port, they have extra ground pin. All the Bruker AFM application module supplied with ESD protection jumpers. We recommend users always leave the ESD protection jumpers connected between the sensor port and test bias port to protect from the damage. Precautions such as grounding up one cell before removing the ESD protection jumper to install one of these application modules is also recommended. For the electrical probe holder, here is the photo. For CFM tuner, tuner 2, TR tuner, and PFOS tuner, they all use the same probe holder. As shown here, this is the tapping piezo or the TR piezo, and here is the probe clamp. Underneath the probe clamp, there is a small piece of metal. Make sure the front side of the probe is conducting and to send the current signal to the sensor. This is the universal connector, and this is the ground wire, which is only used for the tuner 2 module. Here, I would like to share one trick for you to confirm or troubleshoot the holder when you have doubt whether the probe holder is good or not. First thing, you need to connect a small piece of metal or tweezer in a small groove here. Then you need to measure the resistance between the wire connector and the metal or the tweezer. If the resistor is 0, continuity is good. If it is open circuit, then the holder probably is broken or there is some part or the connector is not good soldered. So you need to replace or repair the holder before you're running any experiment. Test resistor. Every application module for current measurement shipped with a test resistor, and this is for testing and troubleshooting purposes. How to use this test resistor? First, you need to connect the test resistor to the module, mount a conductive tip for laser sound, force engage. Second, you need to select ramp mode and display the tuner current while sweeping the DC test bias. Then you need to select the probe calibration resistor and current gain and verify all gain stages are operational. For CFM and tuner module, to adjust the offset and gain, you need to do it manually. So we have discussed the issues we see from the contact mode and TR mode conductivity measurements, and we provide some solutions. If all the solution and optimization technique do not work well with your application or sample under study, you need to find out alternative solution. Now we discuss the recent development in conductivity measurement, both in theory and application examples. Before we talk about the alternative solution of the development, we need to look into the requirement of the AFM-based conductivity measurement techniques. What's the requirement? The first one will be the better force control. As we discussed earlier, the contact mode has high shear and normal force, resulting in many issues. The question is, how about we use tapping mode? Because you all know that tapping mode gives less force compared to the contact mode. The second requirement is to get correlated topography image and current image on the sample at the same time. Now the question is whether we can use tapping mode plus the tuner module together to get desired result. Okay, people have tried, but they didn't get successful in getting a current image simultaneously with the topography, because the tip needs to pack at selected spots and make enough time to take current measurement in contact mode or in the tapping mode. Because the tapping mode is working at around 50 kilohertz, which is the resonance frequency of the probe. So if the result does not work well, we need to find alternative imaging mode. We can use P-force tapping mode. The P-force tapping mode is different from contact mode and tapping mode. It is based on the Z piezo modulation at frequency from 1 kilohertz to 2 kilohertz. So the frequency is reasonably good for the current measurement. For the tuner module, it is a thumb rule that the tuner module must have 10 times faster speed compared to the operation frequency of the imaging mode. For tuner module, the bandwidth is 160 Hertz. So apparently, the old tuner module cannot fulfill the requirement. Therefore, we need to develop new module for this application. So Bruker has developed new P-force tuner module, which has a high bandwidth of 15 kilohertz. It also has high gain from the 20 picoamp per volt to 100 nanoamp per volt. Different from the previous mentioned old module, it has only one mechanical switch to change between high sensitivity to low gain sensitivity gains. And offset and gain is automatically adjusted when the chip is engaged on the sample. You don't have to adjust the offset and gain manually anymore. So this P-force tuner module works on contact mode as well. So it's not only a new module, but can also use for your old contact mode current measurement application. Similar to tuner module, the PF tuner module also can be tested using the test resistor, which was mentioned earlier. Here is an example of the testing result of the sensitivity at 100 nanoamp per volt when we apply the test bias of minus 10 volt to 10 volt. As noted, the gain and offset are automatically adjusted. All that you need to do before your actual experiment is that you need to test the resistor, use the test resistor to confirm the module is working properly and functional. This only takes you about less than 15 minutes. ProSelection. The probe selection guide is similar as before for all the previous mentioned old module. Whatever probe is working well for your old module on your sample, it can be used for P-force tuner module. However, if you want to get sample modulus data accurately or the P-force QNM data, you will need to pay attention to the spring constant and make sure that the spring constant is for the sample modulus range. For the P-force QNM, this is an integrated quantitative nano-mechanical property measurement. Here is a list of the sample modulus and the probe candidate for your reference. PF tuner quantities. Before we talk about the PF tuner quantities, let's see the heartbeat curve of the P-force tapping mode. This is one cycle of the heartbeat curve, which means the Z piezo is ramping to the sample surface at each pixel value. From point A the tip is far away from the surface. So the tip sample surface force is the attractive force. When the tip is approaching to the sample, the force becomes bigger and bigger. At point B, which is the snap-in point, the attractive force overcomes the probe stiffness and come into the contact with the sample. When the Z piezo moving toward the sample surface, the force becomes bigger and big. To point C, the sample the sample and tip forces become the maximum. And we use the feedback of the system to maintain the maximum force. And we call this point C peak force point. After we reach the peak force point, we withdraw the Z piezo, and the force becomes smaller and smaller until to the negative region. At point D, the probe is pulled off from the sample surface, and this is also called pull-off point. When the Z piezo is moving further away from the sample surface, and to point E, this is one circle completed. In the full circle, we can see that we have different contact or different cycle. From point B to point D, this is contact area or contact time between the tip and the sample. So in this contact time, we calculate the current, and this we call it contact current. From point A to point E, this is the tuner current. From point B to point D, this is the peak current. So in P-force tuner workspace, we basically have 3 channels for the current measurement. Here is an example of the tuner current and the peak current imaged on the floppy disk. The left is the high sensor channel data, and the top one is the tuner current, and the bottom one is the peak current. As we can see clearly, the peak current is bigger than tuner current. PF tuner key parameters. How we control the PF tuner parameters? Here are several tips for using PF tuner in the imaging mode. The first one is you need to use smaller P-force set point for soft or delicate samples. Second one is you need to use P-force set point will affect all the 3 reported current quantities: peak current, contact current, and tuner current. So decrease the peak force tapping amplitude will usually increase contact time within each tapping cycle, resulting higher current. If the simultaneous mechanical properties are desired, you need to get the peak force set point sufficient to maintain a 2 to 4 nanometer deformation for the accurate modulus measurement. Next, we will talk about several application examples of the PF tuner. The first example is the lithium-ion battery cathode material, which is L333. In the L333, we also used PVDF, which is a binder polymer, to bind the conductive additive polymer, which is AB, to binding all the conductive additive together to improve the conductivity. From the high image, you can see clearly that there is a L333 particle, but in the current image here, you cannot actually see the conductivity. The pink area is more conductive compared to this area. And we know that this is PVDF and the AB conductive polymer complex. So if we overlay the height and current image, we get this overlay image. So from here, we can see this area is not covered by the conductive polymer. So this is the dead mass in the lithium-ion battery cathode. So this will give some information to improve the process of the fabrication of the cathode material. The second example is PF tuner on carbon nanotubes. The left image is high sensor image, and this one is the tuner current image. The substrate is silicon dioxide on silicon surface. As we can clearly see, the high sensor channel we have several carbon nanotubes, and in the current channel we can see the conductive. And here is the residue sample of the carbon nanotube during the sample preparation. But in the current image, we cannot see this because maybe due to the carbon nanotube is not connected to the conductive pad of the substrate. It is worth noting that while the nanotubes are fragile, it can be pushed about with an AFM tip in contact mode. But here we can see clearly the carbon nanotube and without pushing away by the AFM tip. With PF tuner, the SDM-PIT tip endured for several hours without coating being worn off by the substrate. This cannot be achieved by the contact mode imaging. Another example is PF tuner image on vertical carbon nanotube mat. The left side is the high sensor image, and the right side is the peak current image. As we can clearly see that, we can see the tuner current image correlated to individual carbon nanotube. But we cannot see every single carbon nanotube has the current signal. This perhaps due to the sample preparation, because not every carbon nanotube is in contact with the conductive pad. Or there may be some capping of the tube is not conductive, affecting the measured conductivity. We also do the same imaging with the TR tuner. Here is the comparison of the result. As we can see clearly, the image is hugely different. We can see the TR tuner image. There is several discontinued conductive spots on one single tube, as seen clearly here. This intermittent electrical contact in the TR tuner imaging is likely caused by the lateral twisting motion of the probe in TR mode. That's why we mentioned earlier that TR mode may not be the best option for current measurement. Here is a little summary about the PF tuner. Basically, due to the enhanced force control of the peak force tapping mode, we can achieve reliable nanoelectrical imaging on soft, delicate samples, such as loosely bound nanostructures, conductive polymers. We also obtain improved imaging resolution and tip lifetime while making the conductive AFM imaging easier. Because of the peak force tapping mode, and scan assist, we improve the ease of operation by automatically optimizing the AFM scan parameters. In addition of the above, we get enhanced material assignment on the nanoscale by making use of both QNM and tuner imaging. Here I list the CAFM tuner, PF tuner differences and current sensitivity for your reference. As a summary, CAFM module, tuner module, and tuner 2 module, they are all based on contact mode or TR mode for tuner 2 module. PF tuner is based on newly developed peak force tapping mode. And here is the current sensitivity and current range for your easy reference. Next, let's make a comparison of the AFM-based conductivity measurement techniques in terms of the features. For PF tuner, contact tuner, TR tuner, they are all able to do the conductivity mapping. In terms of the force, PF tuner gives you the best result. The tip sample force can be reached to minimum less than 100 piconewton. While among the 3 modes, only the PF tuner is able to do the quantitative nanomechanical property mapping. Among the 3, TR tuner gives you the difficulty in ease of use. As a summary, in this webinar, we discuss optimizing contact mode-based conductivity measurement, but there is limited options. Alternatively, PF tuner provides reliable nanoelectrical imaging on soft, delicate samples, improve imaging resolution and tip lifetime, while making AFM-based conductivity measurement easier. In terms of the PF tuner application module hardware, it has high bandwidth, no need to adjust offset gain manually anymore. For PF tuner and PF QNM, they are able to get simultaneous and integrated information about current and mechanical properties. As we mentioned earlier, to get the accurate DMT modulus, adhesion, deformation, or the energy dissipation enabled by PF-QNM, you need to do the probe calibration. If you need more information, you can always call us at this number and this email address. This is support.bns.asia@bruker.com. So we provide remote tech support, in-house training, and fast diagnosis and local repair services here. So please feel free to contact us if you have any inquiry. That's the end of my webinar. So now here is the Q&A session. Please feel free to leave your question in the chat box. Okay, we have several questions already. Okay, the first one is, can we get a PDF version of the slides? Of course, yes. I will send you the email with all these PPT slides. Or you can email me at support.bns.asia@bruker.com. We will follow up with email. Okay, we have another question. Okay, what is the fundamental difference between the conductive AFM and the tuner? Actually, the fundamental is based on the contact mode imaging. but the current range is different. CAFM has much higher current range, while the tuner has lower range of current. So the only difference is that the current range is different. Okay, we have more questions coming. What kind of tip should be used for hard disk, which uses magnetic media and DLC coating? So here I have one slide mentioned about ProSelection. So for hard disk, you can use SCMPIT or MEST. But you can also try different probes and find out which one is the best for you. Okay, we have another question. How to do CAFM on semiconductor or insulating substrate? For example, the sapphire and the nitrile gallium. Okay, for very resistive samples or very high resistance sample, we do not recommend to use the CAFM. Instead, we recommend to use SSRM. If you need to get more information about this, please feel free to drop us email at the customer care center email address that I mentioned earlier. And we will follow up with email. And we have more and more questions coming. So I will pick up the last one because of the time limitation here. Okay, does dimension V AFM has the conductivity measurement function you presented? There is a tuner probe. Okay, dimension V system has the nanoscope V nanoscope 5 controller. If you have buy the CAFM or tuner option, you are able to do the CAFM and tuner measurement using the old application module, which is CAFM or tuner module. But if you want to do the P-force tuner, you need to buy the dimension icon system or the dimension FastScan system, plus the PF tuner option. So if you want to get more information about the new system and the PF tuner module, please feel free to email us or contact our salesperson. We will follow up with you. Thank you, Dr. Wang. Okay, I think we have pretty much here, and I will call this the end of my webinar.
Okay, thank you very much, Dr. Jiang. Ladies and gentlemen, that concludes our webinar for today. We hope you have found it informative and helpful. If there are further questions, please email us at the email address shown in the screen now. Before you leave the webinar, we would appreciate it if you could fill a short survey to help us understand and serve your needs better. Thank you very much and have a good day ahead.